This is SpaceTime, Series 23, Episode 32. Coming up on SpaceTime. Claims the expansion of the universe could be different in different directions. The importance of a planetary magnetic field for life. And strange gravity on the asteroid Bennu. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
One of the fundamental pillars of cosmology is the understanding that the universe is isotropic. In other words, everything looks the same in all directions. That is, if you look at it over large enough distances. This isotropic hypothesis is supported by observations of the cosmic microwave background radiation, the very earliest snapshot we have of the universe, taken just 380,000 years after the Big Bang, a time when the universe had cooled just enough for photons to be released as the very first atoms were formed out of the proton and electron soup created by the primordial quark-gluon plasma. A direct remnant of the Big Bang, this cosmic microwave background radiation's uniform distribution in the sky suggests that in those early days, the universe must have been expanding rapidly and at the same rate in all directions. However, new data reported in the journal Astronomy and Astrophysics is challenging that basic notion. Astronomers using observations from both NASA's Chandra X-ray Observatory and the European Space Agency's Newton X-ray Space Telescope, looking at hundreds of galaxy clusters, the largest structures in the visible universe held together by gravity, have noticed that space seems to be expanding at different rates in different directions. The authors used a sample of 313 galaxy clusters for their analysis, including 237 clusters observed by Chandra using a total of 191 days of exposure, and 76 clusters observed by Newton with a total of 35 days of exposure. They also combined their sample of galaxy clusters with two other large X-ray samples, using data gathered by both the Newton and the Japan-US Advanced Satellite for Cosmology and Astrophysics, giving an overall total of 842 different galaxy clusters. The study's lead author, Konstantinos Migas from the University of Bonn, says the observations show there could be cracks in the fundamental pillar of an isotropic universe. Now, physicists generally agree that after the Big Bang some 13.82 billion years ago, the universe has been continually expanding. Now, a common analogy is to think of the expansion of the universe sort of like baking a loaf of raisin bread. As the bread bakes, the raisins, which represent cosmic objects like galaxies and galaxy clusters in the universe, all move away from each other as the entire loaf, representing space-time, expands. Now, with an even mix, that expansion should be uniform in all directions, just as it should be with an isotropic universe. The problem is these new X-ray results don't fit that picture. Based on the cluster observations, there appears to be differences in how fast the universe is expanding, depending on which way you look. Astronomers have already conducted many tests on whether the universe is the same in all directions. These have included optical observations of supernovae and infrared studies of galaxies. And now, admittedly, some of these previous efforts have produced possible evidence that the universe is not isotropic, but most of the studies haven't reached those conclusions. And that's where this latest test comes in. It uses a powerful, novel, and independent technique. It capitalizes on the relationship between the temperature of the hot gas pervading a galaxy cluster and the amount of X-rays it produces, known as the cluster's X-ray luminosity. The higher the temperature of the gas in the cluster, the higher the X-ray luminosity is. Once the temperature of the cluster gas is measured, the X-ray luminosity can be estimated. Clusters of the same temperature and located at similar distances should appear similarly bright. The thing is, that's not what the astronomers observed. Instead, they saw clusters with exactly the same sort of properties, with very similar temperatures, but which appeared less bright than what we should expect in one direction of the sky, and brighter than what's expected in another direction. And the difference was quite significant, around 30%. And the other important point was that these differences weren't random, but had a very clear pattern depending on the direction in which one was observing the sky. Now, before challenging the widely accepted cosmology model, which provides the basis for estimating the cluster's distances, the authors first looked at other possible explanations. For example, perhaps there were undetected gas or dust clouds obscuring the view in that direction, thereby making the clusters in that area appear dimmer. The thing is, the data didn't support that scenario, and the method was independent of cosmological quantities, including the expansion speed of the universe. Once the authors estimated the X-ray luminosities of their clusters using this technique, they could then calculate the luminosities using a different method that depends on cosmological quantities, including the universe's expansion speed. The results gave the authors apparent expansion speeds across the whole sky, again revealing the universe appears to be moving away faster in one direction compared to others. The authors also compared this work to studies by other groups that have found indications of a lack of isotropy using different techniques, and they found good agreement on the direction of the lowest expansion rate. In other words, using different methods, they were still finding the same things. Right now, the authors are looking at two possible explanations for their results that involve cosmology. One is that large groups of galaxy clusters might be moving together, but not because of cosmological expansion. For example, it's possible that nearby clusters are being pulled in the same direction by the gravity from groups of other galaxy clusters. And if that motion's rapid enough, it could lead to errors in estimating the luminosities of the clusters. These sorts of correlated motions would give the appearance of different expansion rates in different directions. And astronomers have seen similar effects with relatively nearby galaxies, at distances typically less than 850 million light-years, where mutual gravitational attraction is known to control the motion of objects. However, scientists expect the expansion of the universe overall to dominate the motion of clusters across much larger distances, up to say the 5 billion light-years being probed by this new study. Now, a second possible explanation is that the universe actually isn't the same in all directions. Maybe that mysterious force known as dark energy is different in different parts of the sky. Now, if it's real, dark energy makes up an incredible 69% of the cosmos's entire mass energy budget, and it seems to be getting stronger, increasing the rate at which the universe is expanding out from the Big Bang. That's based on supernova measurements showing expansion is faster now than what it was 6 billion years ago. So the X-rays may be showing us that as well as being temporally different, dark energy may also be spatially different, stronger in some parts of the universe than others, causing different expansion rates. This would be like as if the yeast in the bread wasn't evenly mixed, causing it to expand faster in some places than others. Now, either of these two cosmological explanations would have significant consequences. This is SpaceTime. Still to come, the importance of a planetary magnetic field for life, and the strange gravity on the asteroid Bennu. All that and much more coming up on SpaceTime. Astronomers searching for planets capable of supporting life look for terrestrial worlds orbiting the habitable zones of their host stars. That's the region around a star where temperatures would allow liquid water, essential for life as we know it, to pool on a planet's surface. But in order to keep that liquid water on the surface requires a thick protective atmosphere, and that requires a magnetic field strong enough to shield the planet from the eroding effects of stellar radiation. And it seems that's actually a big problem in the search for habitable worlds. A study by scientists with the Australian National University on the magnetic fields of exoplanets, that is, planets orbiting stars other than the Sun, found that most were unlikely to be as hospitable to life as the Earth. The sheer strength of Earth's magnetic field helps to maintain liquid water on Earth's surface, thereby making it possible for life to thrive. Scientists modelled the magnetic fields of exoplanets and found very few have a magnetic field as strong as Earth's. Now, they admit that the techniques being used to find exoplanets the size of the Earth are more likely to find slowly rotating planets tidally locked to their host star in the same way the moon's tidally locked to the Earth, with the same side always facing us. Earth's magnetic field is generated by the planet's geodynamo, a molten liquid metallic outer core flowing around the superheated solid metallic inner core due to the planet's rotation. Now, in our solar system, there are 4 worlds in the habitable zone of the Sun: Venus, Earth, the Earth's moon, and Mars. Now, Mars has 2 moons as well, Phobos and Deimos, but like the Earth's moon, they have no atmosphere, and so couldn't hold on to any liquid water on the surface. It would simply sublimate into space almost as quickly as it formed. Venus is almost the same size as the Earth, and it too, like the Earth, has a molten metallic core. But Venus rotates too slowly to generate a strong magnetic field. Still, it does have a thick atmosphere. But any water on Venus would have evaporated away from the surface as the planet descended into a runaway greenhouse effect, with a crushingly thick atmosphere and temperatures hot enough to melt lead, all held in place by a heavy blanket of impenetrable clouds. Finally, there's Mars, which is so small it's lost most of its internal heat, resulting in a core that is now mostly solidified, and so it can no longer generate a protective magnetic field. And that's resulted in the Martian atmosphere being eroded away by the constant bombardment of the solar wind and ultraviolet radiation from the sun. Now, that study's lead author, Sarah McIntyre, says Earth's strong magnetic field played an important role in protecting our planet's atmosphere from the solar wind and keeping the planet wet and habitable. And McIntyre found that most detected exoplanets have very weak magnetic fields, suggesting that it is an important factor when searching for potentially habitable worlds. Astronomers are fairly certain that most stars have orbiting planets. So far, more than 4,000 exoplanets have been confirmed. But most are large gas giants, because they're the easiest to find. The study's co-author, Associate Professor Charlie Lineweaver, also from the ANU, says improving techniques has now allowed astronomers to discover literally hundreds of terrestrial exoplanets, rocky worlds, more like the Earth. Lineweaver says the big question now is whether any of these planets have liquid water on their surfaces, and if so, could they harbour life? To help answer these questions, Lineweaver, McIntyre and colleagues decided to model the magnetic fields of these distant worlds. Lineweaver says strong magnetic fields could protect and preserve a wet surface in a way weaker fields simply couldn't.
Okay, yes, so the first piece of information is, hey, the Earth has a strong magnetic field, Venus and Mars do not. And so what makes a magnetic field? And when you learn about what makes a magnetic field, you have to have a conductive, you have to have a planet that's rotating, you have to have a conducting and convecting fluid inside your planet. That's what the outer liquid core of the Earth is producing, this magnetic field of the Earth. Now, that's fact number one. Fact number two is that when you are a small planet, all planets start out hot and they cool off with time. If you're a small planet, you lose your heat much more quickly than if you're a big planet.
And this is what's happened to Mars.
That's right. Mars is 1/10 the mass, or about half the size, a little bit more than half the size of the Earth, and therefore it probably had a magnetic field in the beginning because it had some type of convecting, rotating liquid core. And then it cooled off, and then it solidified. As a matter of fact, right now in the center of the Earth, that's going on. The liquid outer core is solidifying onto the inner solid core, and that's reducing the amount of material that continues to convect and produce the magnetic field.
I'm assured by geologists that outer core solidification won't be finalized before the sun runs out of energy.
That I don't. I think the time scale, my guess, I haven't looked at this carefully, but my guess would be at close to the same time, within a factor of two of each other.
That's what they're saying, yes. So,
but that might be a fact, instead of 4 billion years from now, maybe 2 billion years from now.
Yeah,
but the main problem with that is not the magnetic field, it's the water that we're losing. That's the thing that's going to short-circuit life on Earth.
Well, the sun will be so hot in 2 billion years' time, there won't be life on Earth anyway.
The increase in luminosity of the sun is on the main sequence has slowed down. And, you've probably heard about the faint early sun paradox. It's the idea that the sun used to be 30% less luminous.
Yes.
But most of that luminosity change was in the first billion years or so. So now the luminosity is only increasing very slowly. And so, but although it's slow, it is indeed the reason why we expect the Earth to lose its water in about 1 billion, plus or minus 200 million years.
Yeah, 800 million years is what I've been told. So, yeah. Okay, so when you're a small planet, you lose your magnetic field more quickly because the core is cooling down and it is more likely to solidify more quickly.
That's right. So that's the reason why we think Mars, although it's rotating at about the same rate that the Earth is rotating, it doesn't have a magnetic field, but we see evidence of a very, very early magnetic field. And so we say, that's consistent with the data that we have. And Venus is not rotating in any. Venus is much more like the Earth. It, too, probably has a convecting outer liquid core. But because of its almost negligible rotation, it's not rotating fast enough to produce a magnetic field.
It's retrograde, isn't it?
Notice that, yes, it is. Yes, but it's also very, very slow retrograde.
Yeah,
it's not. Yeah. If it were retrograde and had a day of 24 hours, then I wouldn't be saying that. But its day is almost comparable with its year. So the idea is, okay, we've got a magnetic field. Venus doesn't. Mars doesn't. We can wave our hands a little bit and say, you know what? This magnetic field of the Earth probably protects us in in some ways. But this is a hot topic in astrobiology. We're not quite sure about this. And now I wanted to do a project about comparing the magnetic field shift on the Earth when north goes to south and south goes to north for a brief period of anywhere from 100 to like a couple of thousand years. There is very little dipole magnetic field strength in the Earth, and therefore cosmic rays get closer to the surface, and maybe that's what would lead to some extinctions. But this hasn't been looked at carefully in the biological data and the extinction data, and I wanted to do that. But Sarah said, you know what, why don't we look at the magnetic fields of exoplanets? But we said, well, wait a minute, we don't know anything about the spinning of exoplanets, but we can make some estimates. And it turned out that most of the rocky planets that are near the habitable zone that are most interesting for this effect we're talking about are tidally locked. And what that means is we know their spin period because it's the same as their orbital period. And then we were able to put together the 3 or 4 pieces from the literature of the people who have modeled the magnetic field strength as a function of things like the rotational rate and the core mass fraction. If you have a little core, you don't make much of a magnetic field, but if you have a larger core, you do. Yep. So anyway, we put together about 2 or 3 ingredients from the literature and then applied it to the largest data set, the largest, newest data set of rocky planets, and then we placed them on a magnetic field strength diagram, and that was the paper. Now, unfortunately, I would like to say that we know how strong a magnetic field is to protect life, but we're not sure of that. But there's circumstantial evidence that, hey, we're on a planet that has a strong magnetic field. Maybe it is associated, and maybe it's protective. And there are good reasons to believe that a magnetic field protects an atmosphere, not just, cosmic rays hitting and changing your DNA, but also keeping your atmosphere from getting ablated.
Which is what happened again on Mars. So.
Well, yeah, we think so. We're not 100% sure about this, but we're finding out more and more about it all the time. And I mean, it is a consensus that hydrogen leaks out of every planet's atmosphere. And when that happens, the ability to make water, because water is notoriously known for being H2O, if you lose hydrogen, you lose the ability to have water. And so anything that protects the hydrogen or keeps the hydrogen from being lost is something that maintains water at the surface of a planet, and that is presumably highly correlated with water-based life everywhere in the universe.
When we look at the flipping of the Earth's magnetic poles, which happens fairly frequently, I mean, it's been a long time since the last one.
It happens a lot, but it's not regular. It's not periodic. There's no periodicity assigned to it.
Every 280,000 years, roughly?
No. The periodicity is not like that. If you look at the striping, the magnetic striping on the around both sides of the mid-oceanic ridges, it looks in artist diagrams as if it is semi-periodic. But I've been assured by people who are experts in this field, and there are a couple at ANU, that there is no periodicity. If you plot a power spectrum of this, you do not see anything that stands out very largely. And so I think it's a little like earthquakes in the sense that you can't look at an earthquake or volcanoes, every 10,000 years this thing. Well, no, it's a hard thing to do. So rather than say it's regular or periodic, it says it happens. You could say it happens frequently. But,
and the degree of fluctuation is different too, isn't it?
Yeah.
Some are stronger than others. It's not always a complete flip.
That's right. And sometimes there have been periods where it just stood out as being, hey, there's no magnetic field for a long time. And sometimes it stays at one polarity for another. The reason why it's so irregular is because it's something associated with the turbulence of the convection in the outer liquid core. So that seems to be something that we don't have a deterministic model for.
Yeah, I think it's got something to do with inverse mountains or something on I guess it would be the floor of the mantle and how that affects
or the roof of the floor of the mantle or the roof of the
inner core.
The inner core, right.
Are you troubled at the level of studies that haven't been done in terms of the degree of species change or species elimination as a result of the changing magnetic poles?
Yes, I am. I mean, that's one thing that I've been trying to get colleagues who would be able to help me do this analysis. We talked about this for an hour a couple of months ago, and we're trying to figure out what's the latest new data set we can use to assess this, and what kind of life form would you see who would be the most sensitive to the non-existence of a magnetic field. So I think it's a ripe topic for a paper, and I may find time to do that.
Okay.
The sample of rocky planets in the habitable zones that we were able to analyze are not a representative sample of all rocky planets that exist. So you cannot make sweeping generalities from our paper. And the reason is because the ones that have been detected are the ones that are preferentially tidally locked. If you're tidally locked, you have a rotation rate that is uncharacteristically low compared to planets that are further away. The reasons that they're tidally locked is because we can more easily see them when they're closer to their host stars, and these are a subset of planets that are closer to their host stars. So we have what's called a biased sample. So although our conclusion is that very, very few of these detected exoplanets have magnetic field strength as strong as the Earth, that is not a representative conclusion based on all rocky planets.
That's Associate Professor Charlie Lineweaver from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Still to come, the strange gravity on the asteroid Bennu, and later in the science report, more confusion about whether you should or shouldn't wear face masks in public in order to help protect both yourself and others from the COVID-19 coronavirus. All that and more still to come on SpaceTime. Astronomers studying data from NASA's OSIRIS-Rex spacecraft orbiting the asteroid Bennu have discovered strange gravitational effects on the 484-kilometre wide space rock. It seems Bennu's shape, composition, mass and wild rotation means gravity acts strange. It exists in a delicate balance between two competing forces due to its weird spin. The asteroid completes a full rotation roughly once every 4 hours, and that rotational rate is speeding up. Now, as Bennu spins up, there's growing tension between the gravity, which is holding things down onto the surface, and the centrifugal acceleration trying to fling things off. The study's lead author, Daniel Shears from the University of Colorado Boulder, says those forces could play an important role in the asteroid's long-term evolution and potential demise. See, the authors found that as Bennu's rotation speeds up, the area around the asteroid's equator is trapped in a gravitational feature called a rotational Roche lobe, something that scientists haven't clearly observed on an asteroid before. Now, a Roche lobe is a region of material that's still gravitationally attached to the object it comes from, but it's starting to get pulled away, forming a sort of teardrop-like shape. And this is where things get really gravitationally strange. If you were, say, standing inside the boundaries of Bennu's Roche lobe and slipped on a banana peel or something, not much would happen. You'd be captured by the lobe and fall down onto the surface. But if you were just outside the Roche lobe and slipped on the same banana peel, you wouldn't fall down. Instead, you'd roll towards the equator, and you could even gain enough energy that you'd roll right off the equator and maybe up into orbit and then into outer space. Now, as if that's not weird enough, it's going to get even weirder with time. That's because radiation from the sun, something called the Yukovsky effect, is causing Bennu to spin faster and faster over time. The Yukovsky effect involves radiation heating up part of the surface. Then as Bennu rotates, that radiation is released again, providing a sort of thrust which increases the rate of spin. It's not much, but over time it all adds up. And as the asteroid's rotation builds up speed, its Roche lobe will also be shrinking, along with the forces that are holding the asteroid together. Now, as that Roche lobe narrows further and further around the equator, it becomes easier and easier for the asteroid to lose material. So far, that material's all been trapped by gravity. But at some point, if the asteroid keeps spinning faster, then material will start flying off into space. In other words, Bennu could end up in the process of spinning itself into oblivion. 10-1955 Bennu is a B-type carbonaceous asteroid with surface spectra suggesting anhydrous silicates, hydrated clay minerals, organic polymers, magnetite, and sulfides. It belongs to the Apollo group of asteroids, meaning it's a near or near-Earth object with an intrinsically dynamically unstable orbit that intersects and crosses Earth's orbit around the Sun. And it has one of the highest known chances of hitting the Earth, with a 1 in 2,700 chance of hitting the Earth between 2175 and 2199. And if it were to hit the Earth, the resulting impact would be the equivalent of a 1,200 megaton thermonuclear device. Launched from the Cape Canaveral Air Force Station in Florida aboard an Atlas V rocket on September the 8th, 2016, the 2,110-kilogram OSIRIS-Rex spacecraft arrived at Bennu in October 2018. OSIRIS-Rex is spending 3 years orbiting the asteroid at altitudes as low as 1 kilometre, mapping Bennu's surface and geology, studying its evolution, its composition, chemistry and mineralogy. And one of the mission's key objectives will involve better understanding the non-gravitational influences such as the Minkowski effect we spoke about earlier. Knowing Bennu's physical properties will be crucial for scientists trying to determine the likelihood of this mountain-sized asteroid actually slamming into the Earth. Research on Bennu has been reported in a slew of papers published in the journal Nature Astronomy and began to flow just 3 months after OSIRIS-Rex arrived at Bennu. Since then, the spacecraft's completed dozens of orbits around the 73 billion kilogram asteroid, using its navigational instruments to measure minute gravitational forces exerted by the asteroid on the spacecraft. Shears says that in July, OSIRIS-Rex will be maneuvered to within a metre of the asteroid's surface in order to use a retractable arm to collect a sample of regolith for return to Earth in 2023.
The main purpose of the OSIRIS-Rex mission is to actually travel to a primitive asteroid, take a sample from it, and then bring it back to the Earth where it can be analyzed in great detail. The main role of the University of Colorado on the OSIRIS-Rex mission is in the radio science experiment. When we send a spacecraft out to this asteroid, it's going to be, millions, billions of kilometers away from the Earth. The only way we can command it, control it, see what it's doing is by sending radio waves out to the spacecraft. The main result from radio science is actually to measure the mass and the gravity field of this asteroid. Bennu has a non-negligible probability of impacting the Earth a few hundred years in the future. The ideal scenario is once we arrive, we take our very precise measurements, we'll be able to determine its location accurately enough so we can say, okay, it's going to miss the Earth by a far distance in the future. If in fact that's not the case, then we need to start thinking about, how would we actually push this asteroid out of the way? You need time and you need to understand the properties of the asteroid. We're really getting some pristine material from the very dawn of the solar system, and we'll be able to bring it in back to Earth and study it in a very detailed manner.
That's Daniel Shears from the University of Colorado, Boulder. And this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. As scientists learn more and more about COVID-19 and how it spread, the advice being given to the general public is constantly being updated. But for most people, that's confusing because it means it's constantly changing. Now, the Centers for Disease Control and Prevention, the CDC, is recommending that people should wear face masks whenever they're in public. It says recent studies are showing that a significant portion of individuals with coronavirus are lacking any symptoms. In other words, they're asymptomatic and may not even know they have the disease. And it seems even those that do eventually go on to develop symptoms can transmit the virus to others before showing any of those symptoms. Now, this means that the virus can spread between people interacting in close proximity, such as speaking, coughing, or sneezing, even if those people are not exhibiting any symptoms. The new recommendations come as a report in the journal Nature Medicine finds that surgical face masks could be effective in preventing the spread of viruses such as COVID-19, as well as the seasonal flu. The findings are based on studies in which patients were asked to breathe into a machine both while wearing and while not wearing a face mask. Scientists found that in the 111 people with confirmed infections, the face masks did reduce the detectable viral load in the air for both seasonal coronavirus and influenza, but not for rhinoviruses, that is the common cold. However, it's far more confusing than that, because a report in the Annals of Internal Medicine found that both surgical and cotton face masks were ineffective in preventing the spread of COVID-19. The study, conducted at 2 South Korean hospitals, found that when COVID-19 patients coughed into either type of mask, droplets of the virus were still released into the environment. The tests involved 4 patients with COVID-19 being asked to cough 5 times onto a petri dish, both while wearing a surgical mask, wearing a cotton mask, and not wearing a mask at all. All the surfaces of the mask were then swabbed, and scientists found COVID-19 on all the surfaces tested. Scientists have mapped the genome of the German Shepherd, one of the world's most popular dog breeds. The study used a blood sample from a healthy 5-year-old German Shepherd living in Sydney. A report in the journal Giga Science says researchers used genetic sequencing to unravel the 38 pairs of dog chromosomes, decoding some 19,000 genes and 2.8 billion base pairs of DNA. The new genome not only provides science with a more complete biological snapshot of this dog species in general, but but it also offers a reference for future studies of the typical diseases that afflict this much-loved breed. German Shepherds are a popular choice in the home and the workplace because of their natural intelligence, balanced temperament, and their protective nature. The problem is, after more than a century of breeding for desired physical characteristics, they've also become especially vulnerable to a range of genetic diseases, including canine hip dysplasia, which is a painful condition that can restrict their mobility. And now to a story which will outrage most of our male listeners. A new study has found that male drivers do pose a significantly higher risk to other people. A report in the journal Injury Prevention claims road safety research has traditionally focused on an individual's own risk of injury rather than the risk they pose to others on the road. So in this new first study of its kind, scientists investigated which types of vehicles and drivers pose the greatest threat to other road users. It seems for cars and vans, the risk posed by male drivers was double the risk posed by women drivers per kilometre driven. And it rose to 4 times higher for truck drivers and more than 10 times higher for motorcycle riders. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.